Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is that great honor and privilege to be serving you here today. As you step back into my virtual classroom, I got a follow-up video from my last one, bullet pointing the pros and cons of solving using all different linear systems methods, all different methods for solving linear systems by graphing, substitution, and elimination. Check out that checklist if you can. I know it's a longer video, about 50 minutes here. This one should be shorter, depending on what I do with it. But just like the last video, what I want to remind you of is you're going into this video having knowing how to solve using these systems already, or accepting the fact that I'll go kind of fast and brisk through. Well, how did you graph that? How did you graph that? What's that whole rise over run concept? Got to find an older video for that, or got to learn it in a different way. This is about why I'm using those certain methods for certain problems here. Sometimes I'll use all three methods. Sometimes I'll just use one or two or what have you, and I'll check them off and let you know what they are. So I have 12 problems here. I'm saving the best for last, as in it's kind of a scattered different look, but the other 11 are random as far as difficulty and as far as when I should choose what for where. I haven't even personally done the problems myself. I generated them for my own students, in fact, for them to do before me, but now I'm going to be doing that for them as well. So let's take a look at these. Let's see which ones seem to be beneficial for me and why I do them. Now, I'll let you know right now I have graph axes reserved for all of these, but I might not use them for all of them. And if I don't use it, I'm just going to delete it and move on. But I have them pre-reserved for scaling and just getting them ready. So this first one right here, I think I do want to start graphing with, because they're both in slope-intercept form. The y-intercepts are in full view right here. I think graphing is a decent option. So I'm just going to go ahead and get started with that one right here. I have a y-intercept of -4 for that first. Let's see how I want to do this here. Let's color code this somehow with different colors. Let's see, I have red, green. Let's use red. Let's use a lighter blue right there. All right, so for the -4, start at -4 as the y-intercept, and rise 5, run 1, etc. Get some of my points here. Looks good. Let's go ahead and draw that line. And then, one of my things in the pros and cons video that I talked about is make sure that you have a good scaled graph axes in there. If you have grid lines and all that other stuff that really helps you be able to plot these points and get this thing done. Because look, I already solved by graphing. It looks like the point's going to be 1, 1. But if I get the true graph here, I want to make sure I get my -1 slope going through. And I can hit all these points very perfectly because I have very perfect axes and my very perfect line tool, which is going to help me do the rest. And not the same blue, but that's okay. So they are intersecting at, let's change that color. Let's say they're intersecting there. Let's use that blue. They're intersecting at 1, 1. That would be my solution set. I'm going to check that for the other ones. And of course, it's good to get that visual and seeing what the graphs actually look like and mean. The other way that I want to solve this one is using substitution. And I'm not going to use elimination for this one because I'm not in standard form and it's not ready. This is close to elimination right here, but substitution, I might as well just be better off. I can substitute 5x minus 4 in for y in this equation right here, and I can solve for x now by adding x to both sides, adding 4 to both sides, and then I get x equals 1 there. Now that I have x equals 1, I can substitute it into either equation. I'll use the top one. Y equals 5 times 1 minus 4. 5 minus 4 is 1, and that's 1, 1, which is what we got before. So the same solution for both sets, whether I graphed or used substitution. It seemed to pan out. I got it, and yeah, that's that. I'll live with it and move on. And again, elimination, it's not in standard form, and that's generally what I'm going to say. If it's not in standard form, I likely will not eliminate. This one's in standard form here, number 2, and I'm kind of in the way of the graph, but you know what? I'm not going to graph this one. This one's the y equals mx plus b's. Yeah, the y-intercepts are going to be decent if I isolate them and make it work. And in fact, I'd rather graph this than use substitution method, I'll be honest, because if I use substitution method, I'm going to deal with fractions. If I graph this with fraction slopes, that's fine. I don't care about that. I'm good with that. But this is elimination ready, despite the fact that the numbers might be a hair bigger for me to make this happen. Now there's x's are ready to cancel as much as possible. 6 and 8 have a smaller least common multiple than 7 and 9 do, and these are negative and positive right now. So I'm going to use elimination for this problem right here, and elimination only. I'm going to multiply the top equation by 3 because 8 times 3 is 24, and I multiply the bottom by 6, or 6 by 4, because 6 times 4 is 24. So if I rewrite these equations here, I'll write this one on top now, 24x minus 28y equals 84, and this equation here will now be, times 3, negative 24x minus 27y equals 81. I'm going to add down the list, the x's go away, and I have negative 55y equals 165. Genuinely, decent trade-off, not having any fractions for being able to, I have big numbers but no fractions. It's a decent trade-off, all depending on who you are. Here's the part I don't love. Negative 3 has to substitute into one of my equations here. I'll do this equation, the 6x one. 6x minus 7 times negative 3 equals 21. What I mean by I don't love it is I don't have a variable isolated right now to solve, but you know what? It's quite okay as well. 6x equals 0 looks like x equals 0. So it looks like I'm getting the solution set 0, negative 3, and I'm just going to accept that for now. And again, graphing's not dreadful, but you do have to rewrite these in slope-intercept form. You have to divide by negatives and avoid the mistakes. The slopes are kind of large. It's like a up 6 over 7 or something like that kind of deal. And I got my solution set in good time. All right, number 3. I'm going to use the substitution method here for sure, and it doesn't look like graphing is going to be one that is set for me to get at this very moment. Even if I wanted to use elimination by moving this thing over, y would still have to be the one to eliminate after some time there. Again, if it's not in standard form for both, I'm likely not going to use the elimination method. Substitution, here we go. Substitute negative 3x minus 5 in for y. I get 8x plus 3 times negative 3x minus 5 equals negative 11. And yes, I have to distribute and all that jazz, but I'm comfortable with this. I've done this for a long time. I'm speaking as like I'm a student. I've done this for a long time in my math life so far, and I think I can just carry through and feel good about it. Get x equals negative 4. And again, if you have questions on how I'm doing these parts here, I combined like terms. I added 15 to both sides. There are the small parts of these problems here that you want to be able to practice solving for a single variable in a single equation through a lot of practice. These are the parts that if you're having trouble, you really want to feel it out and make it work. I don't need this graph anymore, by the way. I'm going to delete that. Not done. I need to now solve for y, which is going to be very simple because I have the isolated variable equation to work with. So y is 12 minus 5, which is 7. I'm going to let you know right now, all the solution sets in here will be integer solutions somewhere between negative 9 and positive 9, and or they'll either be no solution or an infinite number of solution problems. No fraction surprises for answers. No fraction surprises for answers, but, how do I want to say it? But you may deal with fractions along the way. It depends on how you're going to set up a problem with this. Okay, so that's negative 4, 7 for that one. Let me scooch some stuff to the side because I do want to graph this next problem. And in graphing the next problem, hang on, I don't need that work anymore. In graphing the next problem here, I need my face. In graphing the next problem here, I'm going to be doing it out of standard form because these can give me lovely looking intercepts. So graphing for sure. I like all the methods, I'll be honest, even substitution here because isolating y is a quick step away. So I am going to do all three for this one, substitution and elimination. Eliminations, you want to start with elimination? We're there. Add the y's down. We're set. Remember, I'm not just finding the fastest one for all of them. Look, x is negative 4. Kind of almost done now. Let's do 2 times negative 4 plus y equals negative 2. That's going to lead me to, I need a lot of room because I got to do substitution as well. Negative 8 plus y equals negative 2. Add 8 to both sides. Y equals 6. So we should be getting the answer negative 4, 6. I may have made a mistake. I don't assume that I did. I shouldn't assume that I did as a math teacher, but I may have. I'll check it with the graphing in a bit. But anyway, that was ready for elimination. Probably the fastest way. I'm now going to solve by graphing, however. So let's take a look. If it's okay, I'm going to see this better. In terms of graphing, I'm going to go by the intercepts. Maybe you can do this with me mentally here. Hide and divide. X equals negative 1 is an x-intercept for that first graph. Hide and divide. Y equals negative 2 is the y-intercept for this part of this graph. And 2 points make a line. I can go ahead and draw that graph right now. That's obviously not going to be my whole line. I just want to get it as straight through these as possible. Like that. Looks good. Negative x minus y equals negative 2. Play another hide and divide game with this one. Hide and divide. Negative x is negative 2, so x is positive 2. That is my x-intercept for this guy. Hide and divide here. Negative y is negative 2, so y is positive 2 right here. 2 points make a line. I'm going to go ahead and draw that one as well. And, whoa, that's a little dark for my green. And we're going to get a good point of intersection, hopefully, because these graphs are nicely scaled. This is one point. This is one place where you really do want the scales to be working out in your favor, because we only did the intercept points. Notice I didn't go whole slope. Yes, I could have rewritten these, gotten them in slope-intercept form. I probably should have for the one I'm going to solve using substitution for, but, I didn't. Okay, and it looks like it has a point of intersection right here. That's at negative 4, 6. So that seems to line up there. All is good solving by graphing. Substitution method is last here. What I'm going to do is take these equations. I'm going to isolate my y in my top equation because it's already positive y. Subtract 2x from both sides. Y equals negative 2x minus 2. I'm going to substitute negative 2x minus 2 in for y in the bottom equation right there. And I'm going to now get y equals negative x. Excuse me, not y equals. I just started rewriting something. I'm going to get negative x minus the quantity negative 2x minus 2. Good news, those will become positives. Equals negative 2, because there are a lot of negatives now. That's negative x plus 2x plus 2 equals negative 2. Combine like terms here, we get x subtract 2 equals negative 4. Now I can go ahead and solve for y. I'll plug it into that equation. Y equals negative 2 times negative 4 minus 2. I just wrote a 6 because that's my next number I was thinking of, because that's the answer, 6. Minus 2. Negative 2 times negative 4 is 8. Minus 2 is 6. Y equals 6. We get our solution there, negative 4, 6. 3 different methods there, all viable. You can't see any of my handwriting. My face is in the way. Let me hide my face. I'm so sorry about that. There it is. My bad. I don't look at that part of that screen for that thing. I don't always get to see that. That's my fault. So anyway, regardless though, we got the solution set there. We get negative 4, 6 no matter what. Yes, substitution was the longest. But remember, if I wanted to get this in the slope-intercept form here, I could have graphed out of this form as well. So if I wanted to intend on solving by graphing, doing this step could have gotten me there even faster, even though I did it out of order. All right. Going to the next problem and putting my face back on, just because, I am headlining this bit. Yeah, why not do all 3 again for this one here too, in standard form. And this time, if I go ahead and do the graphing, I'm going to play this a little more straight, as in I'm going to probably do substitution first. I don't want to overthink this. I don't know which order I want to do it in. Let's start, let's just start with graphing. But this time I'm going to go ahead and get in slope-intercept form, if you don't mind. The bottom equation in graphing is going to be y equals negative x plus 2. In the top equation, I get negative 4y equals negative x plus 12. Divide by negative 4, I get y equals 1/4 x minus 3. Everything divided by negative 4 there. So these 2 equations right here, remember this can help for substitution. However, that's a 1/4. I'll show you what I can do with that if you were curious. I'm going to graph both of these as follows and find out where they intersect. Let's use my good old red and sky blue right there. So for the red equation, 1/4 x minus 3 up 1/4, get my points in. I'm not even going to draw the line right now. I'm just going to see if these will actually just hit at a spot, because they should together here. Negative x plus 2 is going to be going down like this right here. And it looks like, there we go, that's where they marry. So without drawing the line, you do see where they do connect. It's going to be at 4, negative 2. So my final solution set for this is going to be 4, negative 2. That is solving by graphing. Substitution method. Like I said, I could just set these 2 expressions equal to each other, because if y equals this and y equals that, then I set them equal. If I want to avoid using the fraction though, what I'm going to do is just look at this one that I isolated, and I'm going to substitute that in for y into this equation right there. Gets me to the same set that I had, but I don't deal with any fractions along the way. Distribute the negative 4, you get x plus 4x minus 8 equals 12. Combine like terms, add 8 to both sides, divide both sides by 5, you get 4 for x. Substitute that into this equation, y equals negative 4 plus 2, y equals negative 2. And of course we get that solution set up there. Last one is the elimination method right here. I'm going to multiply the, let's do the bottom equation by negative 1. I'll do negative 1. I'm going to eliminate my x's here. And I'm going to get x minus 4y equals 12, and then negative x minus y equals negative 2. X's eliminate. I get negative 5y equals 10, so y equals negative 2. Playing under the assumption we didn't isolate this just yet here, let's go ahead and plug it into one of these equations right here, like that bottom one. X minus 2, because that's plus y, equals 2. Add 2 to both sides, x equals 4. So once again, for negative 2, we got that all by itself here. Sorry if the video feels fast and or messy, but remember, fast you can pause or slow me down, or once you found your method, you can save it and stop it right there. Okay? Messy, I'm sorry about that. My face is blocking some of it, so I can't tell you. I had to get all of it here. All right, number 6, I'm not going to solve by graphing. I'm not going to solve by elimination. I am going to solve by substitution only. Hopefully you can kind of keep note. Yeah, I don't mind graphing this one right here, but this one will give me a fraction y-intercept. I'm never going to go on a fraction y-intercept. Never, ever. Not when I have other options. Elimination, look, it's the same thing as always. I'd have to move this 2x over and then do a multiplication. At this point, I might as well substitute. Have these take place of y. Negative 3x minus 5 times 2x minus 10 equals 24. And let's go ahead and distribute and have some fun. Negative 3x minus 10x plus 50 equals 24. Combine like terms. Negative 13x subtract 50 equals negative 26. Divide by negative 13x equals 2. Let's delete the graph. Don't need it, but of course my face is in the way. I have to remind myself of that. So substitute into that top equation there. Y equals 2 times 2 minus 10. Y equals 4 minus 10, which is negative 6. So we have 2 comma negative 6. That's the only method I'm going to be choosing on that one. Elimination is not terrible, but again, moving the thing over to maneuver stuff, taking up time. So I'm good on that one. All right, we have one in standard form here. I do not want to graph this one for same reasons I talked about before. Excuse me, fraction y-intercepts. Don't want to deal with them. Graphing is off the table. Let's go ahead, and delete that graph right there. Substitution seems to be off the books as well. If I want to isolate one of my x values or y values, I'll get fractions all over. I'm not going to deal with that, so let's go straight to elimination here. Now, this one's an interesting one if you kind of take a look here. You make the conscious decision, do I want to eliminate x or y? And I think because both signs are negative here, I'd probably deal with the smaller numbers if I can, and I'd say let's eliminate x. But I don't know if you noticed here, as I multiply by negative 2, what's going to happen is I'm going to get a positive 6x, and I'm going to get a positive 16y. Negative 8 times negative 2 is positive 16y there, negative 26. What's interesting about this is if you noticed, I also have a negative 16y in the top equation. And if I have a negative 16y in the top equation, what happens after I cancel these two? Well, these two also cancel out right here. I've eliminated both variables. What does that leave me with? 0 on the left and negative 1 on the right. 0 equals negative 1. And this is one of those cases, when I talked about the pros and cons in the previous video, there's no big tangible idea as to what this just told me. These equations didn't tell me enough, but you know what's happening is both of these lines are parallel. I didn't graph it. I dared not graph it. I don't want to graph it. But if I did, or if I got in slope-intercept form, I'd see both the lines are parallel. And one is like just below the other one. And they never intersect. So what this tells me right here is there is no real solution. There's no solution to this thing right here. These guys will never intersect. So you can't tell with this thing here. You could on a graph, but that's the there's the rub, as we say. I don't mind graphing the top equation, but I won't graph the bottom equation. Graphing's out. Let's happily delete that graph. Less graphing I do, I guess the better. Unless they're already in slope-intercept form or ready to get good intercepts, I'm going to leave off graphing. Substitution's a fine one. I can isolate that y right there. It's going to be a fine one for me to do. I don't mind doing it. For the sake of what I have here, this is really primed for elimination. If I said I'm not going to do elimination when it's not in standard form, substitution doesn't have to happen in this particular case here. I was going to do something with substitution. I don't think I will. So let's go ahead and just do elimination for this one particular problem. Because, no, you know what? I did elimination only last time. Well, yeah, let's do substitution here. Substitution and elimination, but I'll start with elimination. I'm going to multiply the top equation here by -1, and I'm going to eliminate my x's to get -3x minus y equals +1. Bye-bye. Don't need you. 3x minus 3x is 0. They're gone. 4y minus y is 3y, and -13 plus 1 is -12. Divide by 3, we get y equals -4. Now, in terms of solving this thing, let's use, now I want that top equation back again. Come back, Mr. Top Equation. Let's see. Come back, you. I want you. All right, 3x minus 4 equals -1. Y is -4, 3x plus y. Add 4 over, 3x equals 3. Divide by 3, x equals 1. And our final solution set there is 1, comma, -4. All right. All right, and solving this one by substitution, yes, let's go ahead and let's isolate that y up top. That's my preferred go-to here. Subtract 3x over, we'll get y equals -3x minus 1, and let's substitute -3x minus 1 into y in this bottom equation. 3x plus 4, gosh, I'm running out of room. Let me do this, hold on, let me do this down here. It's totally cool with you. Sorry for the mess, but it is color-coded. 3x, I'm doing this equation here. 3x plus 4 times y, wink wink, equals -13. That's 3x minus 12x minus 4 equals -13. Combine like terms, add 4 over. You get x equals 1 when you, 1 when you divide by -9 on both sides. Substitute that into this equation here. Y equals -3 times 1, that's -3. Minus 1, y equals -4. X equals 1, y equals -4. We're back in business there. All right. I have 4 more problems to do. Let's take care of them. Elimination. Nothing but the truth there. Elimination. Now, you might be thinking, how could I add 7x plus 6y and get 21 and 7x plus 2y and get 21? Isn't this no solution? I'd hold your horses on that. You have to think really closely about the fact that x and y could be any number, and there's a very specific number we have to think about with y that might make this work out possibly. So let's play with it. I'll multiply the bottom equation here by -1, and we'll get -7x minus 2y equals -21. So let's go ahead and eliminate the x's. And look, the y's do not eliminate. That's an important facet. If they do not eliminate, that means it's not a no solution. 4y equals 0. 21 minus 21. Okay. Divide by 4, y equals 0. Remember, that's not a no solution. That's y equals 0. 7x plus nothing equals 21, and 7x plus nothing equals 21. What's that x? Let's figure it out. 7x plus nothing equals 21. What the heck is x going to be here? Divide by 7, x equals 3. And there it is. We get 3, 0. Elimination is the only one I'm going to go to on that problem. It's the only one that makes proper sense to me. There's no substitution or graphing to be had for that problem, definitely. Okay, number 10. See, I would love to graph this one because they're in slope-intercept form, but the problem is the y-intercepts are so danged far away from my origin set here, which you can't see behind my face, but so danged far away from my origin set, it's probably not feasible to be graphing with. It's not ready for elimination right now either. This is a substitution exclusive problem for me. I'm only going to substitute on this one here, and in doing so, I'm going to set this in for y, 3x plus 19, equals -2x minus 21. Add 2x over, subtract 19 over, divide both sides by 5, I get x equals -8. Very fast substitution problem on that front. Now I substitute -8 into one equation. Let's do that top one that has positives. Y equals 3 times -8 plus 19. That's negative 24 plus 19, which is negative 5. That is negative 8 comma negative 5. I trust that to be correct there. I'm all good on that one. Substitution only for that one. Graphing should have been fine. The graph isn't big enough. I don't go all the way to negative 21 or positive 19 to make it happen. And that'd be a lot of ups and overs to make it happen. Honestly, I would have still preferred graphing over substitution or elimination. Elimination's not that bad for this problem, but I just would have done it. It's in my blood. Okay. I do want to graph this one, and I think I solely want to graph this one. When there are fractions and you can graph, just go with it. Yes, I could multiply these equations by 2, get rid of the fractions, and do substitution. I could. The only reason why I would not graph is if I find out that these intersect at like a spot like right there instead of a spot on the points. If I did that, then I would do substitution. But I'm going to graph these ones only. I'm going to do the top one in... because I don't have to use the colors purple and green for the other steps. Let's use purple and green. 1/2 x minus 2. I think we had a 1/2 x minus 2 earlier, obviously with a different equation at play. On the other hand, and I'll draw the full graph, meaning I'll connect the line as well. But there's that first one right there. And the whole idea about the graphing with the fractions is fractions are not only not a turnoff for us when it comes to the slope, but it's preferred. Because if you think about it, if you really think about it, we want the fraction to dictate for us our rise over run, right? We want to know how much we're rising and running. Remember, when the number's an integer, I know that you probably know that you just go over 1. There are some people that don't. You know how many people still draw vertical lines when they go ahead and do those ones? They still draw vertical, they go up 2, plot a point, up 2, plot a point. They don't go over 1 as well. 2 means the number 2 over 1. You got to be careful with that thing. All right, these seem to intersect over at this point right here, which looks like it's negative 2 comma negative 2 comma negative 3 right there. That's my solving there by graphing. Okay, and finally, here's my this problem's not too hard, but the point is, this is written in standard form right now, and this one is not written in standard form right now. So it's best that you get them in standard form or something right now. Let's add the 9 over here. Let's do plus 9. Let's make ourselves feel a little bit better about things. And in doing so, we're going to have negative x plus 3y equals 9. So let's just rewrite both those equations right here. 4x plus 3y equals negative 6, negative x plus 3y equals 9. For a grand finale, I wouldn't mind solving using every method. The only thing it's solving with substitution, I'm going to show you something solving with substitution that'll be kind of cool. I'm going to solve using every method on this one here. Graphing, substitution, and elimination. Now, if I'm going to solve by graphing, that means you need to be able to see my graph. I'll save graphing for last. I'm going to start with elimination. Seems like the best way to go. A lot of times I've been multiplying by negative 1 because these are here. Why don't I go and multiply by 4 this time? I know the numbers get a little bigger, but why don't I multiply by 4 here, make it negative 4x plus 12y equals 36. And then eliminate the x's. I got 15y equals 30, and y equals 2. There we go. Now in solving for x here, which way should I go? Let's go this way. In solving for x here, let's do it in the top one right here. 4x plus 3 times 2 equals negative 6. 4x plus 6 equals negative 6. 4x equals negative 12 if I subtract 6 from both sides, and then x equals negative 3. So I'm getting negative 3 comma 2 as the final solution set there. All right, that's solving using elimination. Substitution. Now in substitution, I think ideally what we would do, if we took a look at these two equations that we had here, what most people would probably say is, hey, let's get this x by itself right here, because all the other ones would lead to fractions, and I'd agree, they would. The only problem with the x is now you got to switch the signs after you move the y term over. Not terrible, but there's something that's kind of cool about these two being 3y's right here. I haven't mentioned this in any of my previous videos that I know of. But you don't have to isolate a single variable and get it by itself. What you have to do is get something by itself, an expression by itself that exists in your other equation. If I get 3y by itself in both of these equations, if I make this one say 3y equals negative 4x minus 6, and here I get 3y equals x plus 9, both of these equations have 3y in it. You know, by the way, I didn't have to isolate both of these. I could have just isolated one of them. But once I have 3y equals and the other has 3y in it, that expression can substitute for it. I don't have to divide by 3 here and make fractions out of this. I can make this part here equal this part here. And I can solve this using that substitution. This is the substitution step right now. And now I can solve for x. I'm going to add 4x here. I'm going to subtract 9 here. And I'm going to divide by 5 here. X equals negative 3. Okay. Now in terms of solving for y, yes, I didn't fully isolate y, so I still have to divide by 3 in the end. I'll do it in that bottom one there. 3y equals negative 3 plus 9. 3y equals 6. Y equals 2. So I got my negative 3, 2 once more like I did the last time. Okay, final one I'm going to do here is graphing. And I do not have the room for this thing right here besides my face. I'll hide my face. That's okay. So, kind of narcissistic here. There we go. So let's go ahead and do the graphing stage. Now, in order to do that, let's look at the forms. Where did they go? Let's look at these ones right here. X-intercept for this one would be kind of bad to do. So I'm going to rewrite the top equation in slope-intercept form. So I'm going to get 3y equals, that's not the blue I wanted. Where's the blue I want? There it is. I'm going to get 3y equals, what was it? Negative 4x minus 6. So if I divide by 3, I get y equals negative 4/3 x minus 2. So I'm going to graph this one over here, if you're still with me. Negative 4/3 x minus 2, down 4 over 3, down 4 over 3, and up 4, left 3, as it's a negative 4/3 here. And I'm getting my points, okay? The other one I'm not going to put in that form because I don't necessarily have to. I can graph them by the intercepts only, and I'll be squared away. So start with that line there. That was for this guy, which was in the same color blue, which was an idiotic mistake on my end. I'll make the other one red. That is this guy right here. And I'm going to graph by the intercepts. Hide and divide. Negative x is positive 9, so x equals negative 9. That is one of my intercepts right there. And then hide and divide here. 3y equals 9, so y equals 3. That is my other intercept right there. I'm going to go ahead and graph that straight through. I didn't need to get it in slope-intercept form. And bada boom, bada beam, looks like we're crossing at a certain location, which is right there. And what is that location? Well, hell, it is negative 3, 2. So we have solved by graphing. We have taken care of all of them. I'll let you sit on that one for a second, and then I'm going to switch off the screen in 3, 2, 1. All right, so that ought to do it for that video right there. That was all 1 through 12 you saw me do. Let me count right now. I'm going to do a tally and count how many times I solved using each method. I solved by graphing 1, 2, 3, 4, 5 times. I solved by graphing 5 times. I solved by substitution 1, 2, 3, 4, 5, 6, 7, 8 times. And I solved by elimination 1, 2, 3, 4, 5, 6, 7, 8 times as well. So 5, 8, and 8 right there. So you can tell that the graphing ones, they get reserved there on the back burner. The substitution was very useful in some cases. I liked elimination the most, generally was the fastest, but you can see that all of them have their good methods there. All right, so that ought to do it for me. Go check that other video out before, the one before that was like a pros and cons and bullet point list, so you can really see how I chose to do those other ones. Sorry for the mess on that one particular video though, because I was very low on room. Should have done probably a page of problem now that I thought about it, but you know what? You make the videos next time then. All right, so that's it for me. Take care, guys.